Hello everyone. Let us continue with our discussions on the structure of atom. Now, once the electrons, protons and neutrons were discovered, the question arose as to how these subatomic particles were arranged inside the atom. So many scientists came forward to give their models of atom to explain the structure of atoms. Scientists like J.J. Thomson, Rutherford, all of those scientists, they give their models of atoms. But today, we will be discussing one model, that is the Bohrs model of hydrogen atom. Now, these are the main postulates of Bohrs model of hydrogen atom. The first postulate is that the electron in hydrogen atom can move around the nucleus in a circular path of fixed radius and energy. These paths are called orbits or stationary states or energy states. These orbits are arranged concentrically around the nucleus. So, according to Bohrs model, we have the nucleus at the center of the atom, and the electrons are found to go around this nucleus in certain fixed paths which are called as orbits. Now, these paths are called orbits or stationary states or also called as energy states, and they are arranged concentrically around the nucleus. So, if this is the first orbit, then the second orbit will be like this, then a third orbit. Depending on the atomic number of the atom, it will have different number of orbits like this. The second postulate, energy of an electron in the orbit does not change with time. However, the electron will move from a lower stationary state to a higher stationary state when required amount of energy is absorbed by the electrons, or energy is emitted when electrons move from higher stationary state to lower stationary state. So, as long as the electron remains in its own orbit, it will not gain or lose energy. That means its energy will remain constant. But if some extra energy is supplied to this energy, if it absorbs some extra energy, then it will jump to a higher energy state, to a higher energy orbit. Likewise, if an electron jumps from higher energy state to lower energy state, then it will emit energy. So to go from lower to higher energy state, it needs to absorb some extra energy. If it goes from a higher energy to lower energy state, then it will emit some energy. The third postulate is that the frequency of radiation absorbed or emitted when transition occurs between two stationary states that differ in energy by delta E is given by nu, which is the frequency, equal to delta E, the difference in energy between the two states, divided by h, which is called as the Planck's constant. So suppose we have two energy states here. Suppose this is the first energy state, this is the second energy state. Energy of the first state, let us say, is E1, and for the second energy state, let us say energy is E2. The difference in energy between these two, E2 minus E1, is given by delta E. This represents the difference in energy between the two states. This delta E divided by h, the Planck's constant, gives us the frequency of energy that is either absorbed or radiated when transition takes place. The fourth postulate is that angular momentum of an electron is given by this n h by 2 pi. The angular momentum mvr will be equal to nh by 2 pi. So, the energy of an electron, the angular momentum of an electron in any orbit will be given by this. That means the angular momentum of the electron will be in integral multiple of h by 2 pi. The electron can exist only in those orbits in which its angular momentum is an integral multiple of this h by 2 pi. This explains why only certain orbits or stationary states are permitted. Now, there are some very important points to remember from this Bohrs model of hydrogen atom. Let us see those points one by one. The first point is that according to Bohrs theory for hydrogen atom, the stationary states for electrons are numbered 1, 2, 3, and so on. Just as I represented here, we have the nucleus here, then the stationary states or orbits will be arranged concentrically around the nucleus. These stationary states, they are numbered like this, 1, 2, 3, and so on. The second point is that radii of the stationary states are expressed as Rn, radius of any stationary state represented by Rn is given by n square into a naught. Now n here stands for the orbit number. So if it is the first orbit, then n will be 1. If it is the second orbit, n will be 2, and so on. Now the value of a naught here has been calculated, and its value is equal to 52.9 picometers. So using this relation, we can calculate the radius of any of these orbits or stationary states. If we take the first orbit, then we can write R1, radius of the first orbit, equal to, since it is the first orbit, n will be 1, so 1 square into a, whose value is 52.9. So radius of the first orbit will be 52.9 pm. If the atom has a second orbit also, then we can calculate its radius like this. R2 will be equal to n square. In this case, it will be 2 square into a naught, which is 52.9. 2 square is 4 into 52.9. And multiplying this, we will get the radius of the second orbit also. The third point, the energy of the stationary state of an electron is given by En, which is equal to RH by 1 by n square. Once again, n here stands for the orbit number. RH here is a constant, which is called as the Rydberg constant. And the value of this Rydberg constant is equal to 2.18 into 10 to the power minus 18 joules. So once again, using this relation, we can calculate the energy of these different orbits. If we want to calculate the energy of the first orbit, then we can write A1 equal to minus RH, whose value is 2.18 into 10 to the power minus 18 joules, into 1 by n square. Since we are calculating the first orbit, this will be 1 square. So energy of the first orbit will be equal to minus 2.18 into 10 to the power minus 18 joule. Likewise, energy for the second orbit will be minus 2.18 into 10 to the power minus 18 joule into 1 by n square. For the second orbit, n square will be written as 2 square. So here, minus 2.18 into 10 to the power minus 18 joule divided by 2 square, that is 4. This will give us minus 0.545 into 10 to the power minus 18 joule. In the same way, we can calculate for the third orbit and fourth orbit or fifth orbit and so on. Now, if you just see these energies of the different orbits, you will find that as we go out of the nucleus, the value of this becomes less and less negative. That means the energy is increasing. Least negative means the energy is increasing. So those orbits which are nearer to the nucleus will have lower energy, while those which are further away from the nucleus will have higher energy. The nucleus, the negative sign here for this energy of the orbits indicates that the electrons in these orbits have lower energy than that of an isolated electron. An isolated electron is one which is supposed to be at an infinite distance away from the nucleus, and its value is taken as 0. The energy of an isolated electron is taken as 0. As we go nearer to the nucleus, the negative value goes on increasing. That means the energy goes on decreasing as we move nearer to the nucleus. So these negative signs indicate that the energy of these electrons in these different orbits are lower than the energy of an isolated electron. Now the fourth point is that Bohr's theory can be applied to hydrogen-like species like the ions containing only one electron. For example, helium ion or lithium ion, both of these will have only one electron like in hydrogen atom. So for species like this, which have only one electron like the hydrogen atom, Bohr's theory can be applied. Now the energy of these, the electrons in these species can be calculated using this relation. En equal to minus 2.18 into 10 to the power minus 18 into z squared by n squared, and this will be expressed in joules. Now here n once again stands for the orbit number and z stands for the atomic number. So if it is helium, it will be 2. For lithium, it will be 3, and so on. Likewise, radius of this hydrogen-like species can be calculated using this relation. Rn equal to 52.9 by z into n square. N square, n represents the orbit number, z once again stands for the atomic number of the species. Now, according to Bohr's theory, radiation is absorbed if electron moves from orbit of smaller principal quantum number to the orbit of higher principal quantum number, whereas it is emitted if electron moves from higher orbit to lower orbit. The energy gap between the two orbits is given by delta A, and this will be equal to energy of the final state minus energy of the initial state. For example, if we have an atom here, an electron jumps from this state, suppose A2 to A1. This will be the initial state and this will be the final state. So if electron jumps from here to here, then the difference in energy between these two will be given by energy of the final state minus energy of the initial state. Now, energy of electrons in any state is given by minus RH, which is the Rydberg constant, into 1 by n square, which can be written as RH by n square. So if we have delta E equal to EF minus EI, then delta E will be equal to, for this one, we can write minus RH NF square, and minus, for this E1 also, the energy of the initial state, we can write minus RH NI square. So this becomes delta E equal to RH by Ni square, because this becomes positive, and minus RH by Nf square. So if we take out RH common from here, then inside the bracket we will have 1 by N1 square minus 1 by Nf square. Then the value of RH we can add here. Its value is 2.18 into 10 to the power minus 18. 1 by N1 square minus 1 by Nf square. So whenever an electron jumps from one orbit to another orbit, or from one stationary state to another stationary state, we can use this relation to calculate how much of energy is released or absorbed, or to find out the energy difference between the two states. Now the frequency associated with absorption and emission of photon can be evaluated by using the equation nu, which stands for the frequency, equal to delta E by H. Also, frequency, wavelength and velocity of light are related by the equation lambda equal to C by nu. Lambda here stands for the wavelength, C is the velocity of light, and nu here stands for the frequency. So using the relation that we derived earlier, we can calculate delta E, the difference in energy, and once we calculate this delta E, we can calculate frequency, and after calculating the frequency, we can calculate the wavelength using this relation. Keeping this in mind, let us try to solve some problems. The first one, so we have delta E equal to RH into 1 by Ni square minus 1 by Nf square. So RH, its value is 2.18 into 10 to the power minus 18 joule. Since the photon jumps from fourth state to the first state, this will be the initial state, this will be the final state. So this will be 4 square minus 1 square. So this gives us 2.18 into 10 to the power minus 18 into minus 15 by 16. On simplifying this, we will get minus 2.04375 into 10 to the power minus 18 joule. This gives us delta E. Then frequency will be equal to delta E divided by H. Delta E has been calculated here. H is the Planck's constant, whose value is 6.626 into 10 to the power minus 34 joules second. I want you to try and calculate this frequency. Delta E, we have calculated here, then H, its value is here. So using these two values, you try to calculate the frequency. After you calculate the frequency, you can calculate the wavelength also. Since we are asked to calculate frequency as well as wavelength here, wavelength will be given by C by nu. C is the speed of light, that is 3.0 into 10 to the power 8 meter per second. You calculate nu, the frequency, and put its value here to divide the speed of light, C. Then you will get the wavelength. I want you to try and calculate this. I'll give you the answer in the next class. That's all for today. Thank you.